Nun stelle ich Ihnen Professor Dr. Nicola Scafetta vor. Steht schon bereit hier an der Bühne. Professor Dr. Nicola Scafetta ist Physiker und Professor für Ozeanographie und Atmosphärenphysik an der Universität Federico II in Neapel. Er hat 2001 an der University of North Texas in Denton, USA promoviert. Professor Scafetta forscht zum Klimawandel, der Veränderung in der Atmosphäre und den Ozeanen. Er forscht zu dem Zusammenhang zwischen der Sonnenaktivität und dem Klima sowie zu anderen geophysischen Phänomenen. Sein Arbeitsgebiet erstreckt sich auch auf theoretische und angewandte Statistik und nonlinearen Modellen komplexer Prozesse. Professor Scafetta veröffentlicht regelmäßig in einer Reihe von Fachgebieten wie Astronomie, Biologie, Klimatologie, Physik und Soziologie. Aber anschließend wird er jetzt weiter zur Sonne berichten, wie bereits sein Kollege Dr. Willi Sohn. Er hält jetzt einen Vortrag zum Thema empirische Bewertung der Rolle der Sonne im Klimawandel anhand ausgewogener multi-proxy-Sonnenaufzeichnungen. Ich heiße Ihnen herzlich willkommen, Dr. Professor Nicola Scafetta.
Okay, do you hear me? Okay. So I would like to talk about this topic now. I will try to add something to what Willy soon have said, and I will show you some of my interpretation of many other things. Okay, I have two talks here. I am going to talk about this paper, which of course has been published just last year. It's very recent, but of course it's a paper that builds on many other papers that I published in the past. So let us see what I am able to argue. Okay, the issue is that how much will the Earth warm? This is the goal. Okay, everybody would like to know this. I don't think that many people are really want to know about the sun, but they want to know this because this is what quantify the danger of climate change. Okay, and then the politics and so on. So the final end is this, but we need to understand the sun. So that is the problem to get there. Okay, so let's go here. Okay, so what is this? This is the temperature of the Earth, the history of the temperature of the Earth, 500 years, 500 million years of the Earth, and you see, of course, that the climate have changed a lot. So we can say that climate always changes. Okay, nobody really question the issue. But the interesting thing is that when you analyze that record, you start to find a lot of cycles. So we find cycles that are about 150 million years, cycles that are about 30 million years. Then we find a number of cycles that are actually well known, which are related to the variation of the orbits of the Earth. So cycles associated with the eccentricity of the orbit, of the obliquity of the axis of the Earth, the precession of the Earth side, and so so these are the Milankovitch cycles. Then we start to see a set of cycles that are around thousands of years cycles, several cycles. So we will talk about the Bray-Alstat cycles of 2,300-400 years. Then we have millennial solar cycles, and then we have other 100 cycles, 200-year cycles, cycles that are around 90 years, then 60 years and so on. Then we have also some effect of the moon, and then we have a smaller, shorter cycle. So there are a lot of cycles, and the interesting thing is very likely all these cycles have some astronomical origin. Okay, so that's some astronomy. This means that if we would really understand climate change, we need to study astronomy, astrophysics. Okay, and that is, in my opinion, one of the reasons why most climate scientists don't really get climate change, because they do not know astronomy. Okay, they do not know astronomy, and that is the problem. Oh, now Okay, so this is what we would like to understand. Okay, this is the temperature of the Earth. We have here that the Earth has warmed about 1 Celsius degree in 160 years, something like that. The problem is that whether or not this warming has been due to nature or to humans. Okay, so that is the big problem. The IPCC, we have seen before really soon, the IPCC claims that the climate have changed during these 150 years because of a set of forcings. And among all forcing, they actually add 2 natural forcing, which are the solar forcing and the volcano forcing. Then everything else is claimed by definition to be anthropogenic. And so they say, okay, the solar forcing is this one, then the anthropogenic forcing is this one, and so on. It is evident that climate change is due to humans. Okay, so if you see this picture, there is no doubt of that. So we have seen that sun changes very, very little, therefore does not matter much. Here in these graphs, these are the forcings. The sun is this curve that you see here. Okay, this is sun, this curve that this here, and you see that is very, very little. You don't see even either. You don't see the sun effect here compared to everything else, which is anthropogenic, except this one, which is the volcano, this with these spikes. Okay, this is the volcano. Okay, but everything else, the trend is essentially due to human so-called forcing. Okay. And this is the main picture, the main argument that the IPCC does. So they use these models. These models are run in 2 ways. In one way, they are running with all forcings, both humans and anthropogenic. And in another case, in another experiment, computer experiment, they are running only with solar and volcano forcing, which are the natural one. And they claim, look here, so if we use only this forcing, we get these curves. Okay, so we get these curves that is practically flat. As you see here, it's practically flat, so natural forcing is not able to produce any warming, while when we use all forcings, then we get the warming, the observed warming, which is the black line. Okay, so that is, and then so they conclude that humans have contributed 100% of the warming. So this is the anthropogenic global warming theory. But there is a problem here. There is a big problem. The problem is that in this argument does not prove anything, because actually here there is a huge violation of the scientific method. Okay, scientific method. Why? Because the scientific method requires that we compare the prediction of the model with the data, with the observation. That is what the scientific method is all about. We can create whatever we want, any model we want, but then we need to demonstrate that the prediction of the model coincide with the observed data, with the real world. And here we have a comparison actually between the prediction of the model and the data. The problem is here. Here there is the model, but there is no data. So practically, to prove this prediction of the model, we need a planet B. We need a planet without humans. And do we have a planet B? No. So we do not have they tell us this. No, we do not have a planet B. So we don't have the data to prove this prediction. So here we do not know whether or not this is true. If the models are correct, it's okay. But if the models are wrong, we don't know from this picture. Okay, so we do not know. So this actually does not prove anything. Does not prove anything, because we don't have data to back up this prediction. This argument assumes that the models are correct. Assumes. But we need to prove that the model is correct. We cannot just assume that the model is correct, okay? So that is a big violation of the scientific method. And okay. So let's us look at the sun. Okay, could the IPCC have underestimated the rule of the sun? So we have talked a little bit, but we need to show evidences that this might be the case. If not, okay. Okay, so let us these things. Okay, so let us look at the IPCC itself. Okay, so I don't want to show you what I got. Okay, then I will show you what I got. Let us first look what they have published. Okay, this is the picture 3.2 at page 432 of their last book, no, AR6. And they've published this picture. Okay, so this is what this is 1,200 years of data. The data are the black one, the gray one. Those are the data. That things there. And then there are the models that are these colored curves. And what do we see here? Okay, it seems that more or less things are good here. Then be careful. The red models, CMIP6, these are the latest models. Okay, these are the models that are believed to be the best one. So this is the red one. So okay, more or less things are good here, good here. Okay, the data are here, and the models are here. Okay, so this is what is known as the medieval warm period that more or less exists in the data. Now I don't discuss this data. I will do that later. But here we see a clear difference between the data and the model. So according to the IPCC models, the medieval warm period was as cold as the Little Ice Age. Okay? This is what the models are telling us. Okay? Because the models show this are here, the data are here. And they say that in the IPCC record, they say before the year 1300, larger disagreements between models and temperature reconstruction are expected. Okay, because forcing and temperature reconstruction are increasingly uncertain farther back in time, but specific causes have not been identified conclusively. Blah blah blah. So they realize that here they have a problem. And this is a huge problem because this means that these models are not able to reproduce the hot period of the past. And here we have another hot period. So if the models are not able to reproduce the hot period of the past, that means that they don't have the mechanism capable of reproducing the hot period of the past. So we cannot even trust that what they are doing here is correct, because the warming that we see here could have been caused by the same mechanism that is missing here. Okay, so that is a big problem. And the IPCC should have actually read better my own paper, because actually I published these results some years before the IPCC. So what we see here, these are the models, and these are the data. So you see that once that you assume that the solar forcing is very, very small, you get what you have found before, no? So you get this, okay? You get this. But this continues for thousands of years. It's always flat. Climate does not change. So according to the models, without humans, the climate is practically constant. It does not change. We have seen before that it always changed in time. So here there is a huge problem, and the IPCC realizes that here there is a problem. They realize that here they have a problem, but then they don't have, I do not know, the honesty or perhaps the knowledge for realizing that this problem put in question their own model. In particular, the CMIP6, okay, that are used for the prediction. Okay. Medieval warm period, okay, I don't spend too much time with this. It is very well known that it was warm. We find on the Alps, we found a lot of wood where now we find there are glaciers. Okay, so we find the wood under the glaciers. So that means that we had warm periods. This is what scientists believe that was during the Roman warm period. So this is the Susten Pass in Switzerland. That is believed that was like this with some trees. Now it's like that. There is nothing because it's too cold for trees and so on. And this is some reconstruction. Okay, so what caused the warm period? So the only thing that has a pattern similar to the temperature is actually the solar record. The solar record. So you see here in the top, you see this one solar record. Here you have the temperature, reconstruction of the temperature. So we have modern warm period, little ice age, medieval warm period, dark ages, cold period, Roman warm period. The things more or less match with the same modulation of the solar record. Okay, solar activity was high during now and during the Middle Age, during the Roman period, and so on. This is actually a reconstruction of the temperature of the summer European temperature or Europe, and you see that okay, warm period now, cold period now, warm period, cold period, warm period, with warm periods that are comparable to 2000. Okay, so we are here, so more or less we get this warm period in the past. So the things, it seems that there is a cycle here. There is a cycle here. There is a cycle, okay? So what will happen here? And the solar activity actually has this 1,000-year cycle. This is a solar record from C14. So we see this millennial cycle that coincided more or less with the temperature cycles. And when we compared the data, solar record with the climate data, we found some very good correlation for thousands of years. Thousands of years. Okay, so it seems that the sun is the big guy here somehow. And other papers, many papers, show the same strong correlation for thousands of years. Okay, Kerr, a variable sun paces millennial climate in science in 2001. So these are the papers say the same thing, and so on. These are the temperature on the Alps. That is important because this is the temperature of the Alps. Warm period now. Cold, warm, Roman period. Cold, warm, cold, warm, cold, warm, cold, warm, cold, warm. Okay, let us say now 1,000 years ago, 2,000 years ago, 3,000 years ago, 4,000, 5,000, 6,000, 7,000, 8,000. Do you see a millennial cycle here? You see something that goes up and down. So, this warming that we got here, according to the IPCC, is due to humans. But here it appears as cycles. It goes up and down, up and down, up and down. So it could be predicted, actually. Then we will see. Okay? The sun is the same thing. This is a paper from McCracken. Okay? These are some solar data. And we found the 1,000-year cycle here. The 1,000-year cycle. 1,000-year cycle. But we find also another big cycle, 2,300-year cycle. Then we will talk about it. We found a 200-year cycle, and then there is other things. Okay, so we find cycles, long cycle in the solar activity, and therefore the idea, Laura. So we need to ask ourselves, what is the cause of these cycles? What is this? So this is the root for understand everything, to understand climate change, also climate change, because so of course the sun is an oscillator somehow. There are 11-year solar cycle, but we need to understand this oscillator. because when we have a system that is oscillating, or we have a system that is oscillating by itself, or we have a system that is oscillating because it is forced by some oscillating forcing. So the system synchronizes with the external forcing. And so I would like to investigate this second hypothesis, okay? And we go back in history. So this guy is a Wolf, and he's the guy who actually constructed the solar sunspot cycle. So he find out that there is this 11-year oscillation, okay? And so he asked himself, what is the cause of this 11-year oscillation? And he had some idea, no? So he wrote here, okay, he had a conjecture that the variations on sunspot frequency depend on the influences of Venus, Earth, Jupiter, and Saturn. So he was claiming that perhaps the sun is oscillating because it is synchronizing with some gravitational forcing, or in any case a forcing associated with the planets, and so that was putting it in oscillation. And actually, the idea was, in my opinion, not bad, because it is possible to construct some model that they show up, the planets show up in some sense. For example, if we take this record, sunspot record, and we calculate the spectrum of this record, we find a strong peak around 11 years, but we find also these other two peaks here and here. And it happens that this peak is around 11.86 here, and this peak is around 9. Almost 10 years. And these two peaks, actually, this period is the period of the orbit of Jupiter. This is the period of the spring tide between Jupiter and Saturn. Then we have other models that we can build. These models use also use the Earth, Venus, and Jupiter. So they somehow calculate the combined effect of the three tides, and these three tides create this red model that oscillates with an 11-year cycle that matches actually the 11-year cycle of the sun, which is the black one, okay? It matches right well. It matches right well. And therefore, we can actually use these three periods here, okay? These three periods here to build a harmonic model of the sun. So we have three cycles that are together, and therefore there are some conflict between the sun. Okay, sometimes the cycles are in phase, sometimes the cycles are not in phase, so they are they destroy each other, and therefore we find out that these three cycles are able to build this red curve. And the interesting thing is that this red curve, obtained by the bits between these three cycles, create an almost 1,000 years oscillation, It creates also this kind of peaks. And these peaks actually match quite well with some warm period during the past. So they match quite well also with the data. This is a zoom of this record. So you see the data, the temperature data, and the red curve of this model, where we have high, low, Maunder minimum, high, low, Dalton minimum, high, low, and then high. Then the sun is going a little bit down, and so on. So we have some kind of correlation between these models. Actually could predict this low activity, solar activity here. Okay, But I did something more than that. So if we take the 4 planets, major planets that are Jupiter, Saturn, Uranus, and Neptune, these, while moving around the Earth, around the Sun, they create some kind of pattern in the gravitational field. So you see the gravitational field can change, okay, according to the position of the planet. So this creates a lot of resonances. And in particular, there are some particular resonances that are defined by this equation. And in particular, there are some resonances which are actually invariant in the sense that they do not depend on a rotating system. And so we now study the resonances, the invariant resonance of this system. And we find these cycles. These are some cycles derived from this. These are some periodicity. And so we get a lot of interesting periods, but let us compare that with the data. Okay, these are some paper. This paper compared the solar and climate record. So we have that the solar record and the climate record show cycles around 46 years, 56, 7 years, around 91 years and 90 years, around 206 years, around 1,000 years. So these are the eddy cycles, De Vries cycles, Gleisberg cycles. Then we have a set of 60-year cycles, 45-year cycles. These red spots that you see here, these red figures here, are these numbers, are these resonances obtained with the gravitation, okay? Obtained with the gravitation. You see that they more or less match with the same cycles that we find in both solar and climate records. Here there is a comparison between a cycle, this is the cycles obtained with this harmonic, which is another resonance, a gravitational resonance, with the Hallstatt cycle found in the C14 record. And you see that there is a perfect matching between the two cycles, okay? The perfect matching between the two cycles. One is experimental and the other one is theoretical, okay? And so what is this? Is that a coincidence that the sun and the climate are oscillating with the same frequencies that we can find in the solar system? I don't believe so. I believe that there is something very interesting here. And there is another study that I did so I'll go to look what happened to shorter cycles. So here I compared the cycles in the global surface temperature and during the last 150 years with the cycles, the gravitational cycles of the solar system, which are here, and we find some interesting thing. Here we find 60-year cycle, and here we find a 60-year cycle. Here we find a 20-year cycle, and here we find a 20-year cycle. Here we find a 14-year cycle, and here we find a 14-year cycle. Then here we find this signature. This signature is the 11-year solar cycle, okay? And we saw before that the 11-year solar cycles can be related with these two cycles, which are Jupiter cycles and Jupiter and Saturn spring tide. So there's this. Then here we have a 9-year cycle, which is missing here. I will talk it in 1 minute. Then we start again, 7.4-year cycle, 7.4-year cycle here. Then here there is another cycle, here there is another cycle, there. So practically we have all these cycles in the temperature coincide with cycles that we find in the gravitational field of the solar system. These cycles in 9-year cycles, but this is easy to find out that this is associated with the lunar orbit, the moon orbit. Okay, so I will not talk about that. So practically, the climate system is oscillating with the same cycles that we find in the gravitational field of the solar system, and we find some confidence. So this is the quasi 1,000-year cycle that deduced from astronomy. And we find here comparison with the data, okay? So you see that there is a match, rather well match, okay? This is not a fitting, so this cycle is poorly deduced from astronomy, and that is another comparison with the solar record. So we find these things. Now there is a lot of things here because we need to understand how could the planets eventually influence the sun. I am not going to talk about this, it's complex, but the idea is that the sun somehow is amplifying a lot the planetary effect up to 1 million times, and so I am not going to talk about this, but there are papers, okay, on this stuff. Okay, so what is wrong in the climate models? Why they don't get the medieval warm period? Of course, they don't get well the solar forcing. Solar forcing is very interesting. We have seen that there are many possible choice for solar forcing. The IPCC chooses that record compared to the others. Here there is an issue regarding what happened during the last 40 years. We have the acrim reconstruction of the solar activity against the PMOD reconstruction, and the big issue is that what happened here during this period. So we have the acrim 1, the acrim 2 data. Here we have the nimbus data, and you see that this data actually look different from this, right? The reason is that this group have altered the original data. These are the original data. These are altered data, so they claim they are to be correct, but if we look at the real data, the sun went up and then went down. Okay, so we have a lot of confusion here about what the sun did, and the IPCC uses this record that is very, does not vary much, but there are many other records on the table. So this is a big difference between what they use and what could be used. And there is a problem. Okay, here there is an interesting things. I took this paper because we are here near Germany. Solar modulation of flood frequency in Central Europe during spring and summer of interannual to multicennial time scale. They find out a very good correlation between solar record and the floods in Europe. Very, very good. For thousands of years. So, but the floods are due to what? Are due to rain, right? So here there is some connection with the cloud. There might be some connection with the cloud. So it seems that the sun is somehow influencing the cloud system, which produces rain, of course. And okay, we have evidence that solar activity, there might be credible, strong evidence, in my opinion, that Svesmark will talk about, that actually the sun may be influencing the climate in a very strange way, because the IPCC, in the models used by the IPCC, only assume that the sun influenced the climate via light, okay? Via light. But there might be another mechanism that for which the sun could influence the climate, and is by a modulation of the cloud system, a direct modulation of the cloud system by a particle forcing, which is modulated by the magnetic field of the sun. So this mechanism is completely missing. The problem is that if we believe data like this, they may suggest a very strong connection with the cloud that are directly influenced with the sun somehow. And that's created a problem in the sense that the sun may be influencing the climate system in two ways. One, via the variation of the light, and two, via other things associated with its magnetic activity. Therefore, it is not possible to assume that the climate system is sensitive to solar changes in the same way how it's sensitive to greenhouse gases, which are just radiative forcing. And therefore I did this model. Okay, so first of all, here I put different kind of solar forcing, because we have different kind of solar forcing. Then we have the volcano, we have the anthropogenic forcing, and I run this double experiment. So in the first case, I use the forcing in the same way how the IPCC models are doing that. So they are assuming that the sun influences the climate system only via light, and they are using this forcing, which is very low variation force. It's almost flat, okay? So by using those hypotheses, I get the same results of the IPCC. So the sun does not produce much warming. Most of the warming is due to anthropogenic forcing and so on. But if we use this other forcing, which is another possibility of solar forcing, okay? Another possibility of solar forcing, and we do the hypothesis that the climate system might be sensitive to solar activity in different ways. So might be sensitive to the light change, but also to magnetic activity from this direct modulation of the cloud system. So we can get this kind of results. So we get that the solar signature now appears like this, much stronger, almost compatible with the anthropogenic forcing. Then we have the volcano, and we get essentially a much better match with the data. Here you see this comparison. These are the models of the IPCC. Okay, they seem to be good, but they are not good really. This is the comparison with the other model, and you see here that the model actually show a modulation that matches the data much better than what the IPCC model are doing. And this model implies something interesting, because it implies that the solar effect on the climate is due to about 20-30% to difference in light, and the other 70% to another mechanism, which is probably associated with this magnetic activity that influences the cosmic ray or other particles, which means that the IPCC models are completely missing the main mechanism, which is associated with a direct modulation of solar activity with the cloud. Okay, a direct modulation of solar activity of the cloud system, which are the main things. So let us put together all that information. Let us put together the cycles. Now I am using a models with the cycles, because I have identified those cycles that I have shown you. I am putting here anthropogenic activity. I put here volcano, okay, but the volcano don't see too much. So I get this model that is very matches pretty well the data, and there is this oscillation. This model show that 50% of this warming until here is due to the sun, perhaps 50% to humans, perhaps, but we will talk this tomorrow. And then what happened with this model? I can go ahead with this model, because I have a model for predicting solar activity, and I have a model for predicting a scenario for anthropogenic force. I get this simulation. Why this is important? Because by the end of 2100, these simulations are within the Paris Agreement. And that means that very likely there is not alarm. There is not a climate crisis. I will talk this more in detail tomorrow, okay? But the conclusion of this study is that if the sun is a big guy here, then climate is mostly regulated, is significantly regulated by the sun via cycles, and that means the human activity must be reduced drastically, and therefore in the end, the simulation show us that there is no crisis because we will remain inside we will satisfy the Paris Agreement with without using the net zero policy. Okay, that is the point. The net zero policy are not necessary. It is demonstrated in the scientific literature published just a few months ago. Point.